Yeah, so welcome to this first hybrid seminar. And for like the first hybrid seminar, I think it also makes sense to talk about the hybrid quantum algorithm, particularly in theme. So I'll be talking about some work that I did for my graduation project, which I also did here at QuSoft, which started at the beginning of 2020, I think. So solving correlation clustering with QAOA and the Rydberg qudit system, a full stack approach. There's also a lot of co-authors, which two are actually here in the also in the room, so GC and Florian, who supervised me at that point. And the article is now in archives, currently under review. So yeah, motivation for this will be like a NISC focused talk. So when I started, so in 2020, the beginning of that, we just had this Google supremacy experiment. So computers could actually do something which we think complex computers couldn't do efficiently, at least not efficiently after 3 days. Turns out later. And then the natural question to ask is, of course, in this setting, is there also like some practical advantage for some kind of problem possible in this NISC area, which we at that point maybe still believed, or maybe still believe will be possible. And QuSoft also just started collaborations with industry, and that's actually where this project originated from. So already then it was pretty clear intuitively that noise severely limits your algorithm performance. Actually, this was made more on a more content level, made concrete in 2020. It actually was also expected intuitively. If your depth grows with your circuit, then it severely limits performance and probably inversely proportional to the error. So the depth you can go goes inversely proportional to the error that you actually achieve in your system. Yeah.
Shouldn't the error go up with the number of gates?
Yeah, so the point is, so if your error goes down, your depth can grow. So also if your depth can become bigger, your errors become smaller. So,
but I would think that you can only tolerate 1/p number of gates.
Oh, did I write it wrong? That makes sense, right? So if your error goes down, then your amount of gates you can do goes up.
Yeah, that's not what I'm saying about.
Oh, sorry.
Like every gate, suppose you have 20.
Yeah.
Every gate introduces some error.
Yeah.
Right? Suppose you have 20 qubits, you have 2 gates. That means there's 10 for each one.
Oh yeah.
There's 10 gates.
Yeah.
Which means you get like 10 or maybe 20 sort of portions of error.
Yeah, I fully agree. I think here in this result, actually assume that at every step you only do like 1 gate.
Oh.
So yeah, of course, it makes sense if you put in the same layer, you put more gates.
So that equals number of gates here.
Yeah. Of course, because if you do more gates in the same layer, then it's more prone to error than doing a single gate per layer. Yeah. Good remark. We actually also show this later in the result. We actually showed the functions number of gates. So only assuming 1 gate per layer. So basically, it's very natural to you actually have to optimize both your interplay between software and hardware in order to get the most out of it. In the setting where noise, every other step you do is going to severely limit your performance. So we believe that actually a very good way to approach the setting will be to take a full stack approach. What we mean with this in the setting is actually that we actually start from a top-down approach. So you first have your problem that you define. Then you're gonna, of course, choose your favorite quantum algorithm to solve this problem. Then you also consider the whole compilation, the process to design, the gate design, try to optimize the interplay between those two to get the most out of it. And finally, do some performance analysis. So basically, I've actually here I've added a picture of actual hardware. This is not what we're going to do. We're going to do everything we can do before the actual hardware implementation. So we're actually ready with everything before we can actually run the actual experiment. So that's a general idea. We call this the full stack approach. And every time I will actually refer to this full stack to show where we're currently at of the stack in this the process that we will walk through in the setting. So first, the problem that we wanted to solve was actually originated from this QuSoft industry collaboration, and it came from Bosch. And the problem that they were interested in was this multiple person pose estimation problem. Basically, the input to your problem is some kind of picture containing people, and then you have some neural network that actually detects some body parts candidates. And basically from this set of candidates, it constructs a very dense graph. So every node here is a certain body part, and the weights between its edges indicate some relation between these body parts. So how much the neural network feels they should belong to the same person. It's then all classical pre-processing. I mean, this is all classical in this setting. And from this, you can construct an integer linear program from which you want to extract two different features. Namely, you want to label the body parts. So for every node, which kind of body part is it? Is it an arm? Is it a neck? Is it a leg, for example? And you also want to know to which person does this body part belong, which you can see in this A part of the figure. Those are person clusters, so indicating which body parts belongs to which person. And then finally, from this information, you can construct a pose estimation, which is then the output of the algorithm. And this integer linear program is actually a generalization of a very well-known problem in computer science, which is called the correlation clustering problem. And it's formally defined in this way. So you have a graph of a set of nodes V and edges E, and it's undirected. And let's say we have n nodes. And then the clustering is a mapping basically from the elements to be clustered, which are nodes, to a set of cluster labels, which also is the same size of the amount of nodes when you actually start the problem. And basically say this mapping is the same for two nodes that belong to the same cluster. So they're part of the same set. And given two edges, I think two weights. So here they talk about like positive and negative weight. You can consider a single weight. So here they basically say you have a weight for association, for like not associated. That's on a plus and a minus weight. We can also consider a single weight where the plus would indicate you want to be together, and the minus would indicate those two nodes don't want to be together. You can create two equivalent problems, so where you want to maximize one vector function and also minimize one vector function. In the exact setting, they're exactly the same. So the maximization problem here is the same optimal solution as the minimization variant, but they're different, as is very often the case in these kinds of problems in the approximation setting. And so they're called min disagree and max agree. And yeah, so view this, so like the graph setting, just view this as being having a graph of certain nodes where you have edges that are either positive or negative. And positive means they want to be together. Negative, it means that the nodes don't want to be together in the same cluster. And actually put them in, for example, give them labels, for example, here colors, which indicates that they're in the same cluster. And then basically here you get the clustering. And the way that I've written down this example, you see every time there's a plus between the three different nodes, they're in the same cluster. And every time there's a minus between, they're in a different cluster. In this particular example, we have a perfect clustering. Yeah, yep.
The example with the body parts, do you already have a number of clusters you're looking for, or is that something?
So that's a variant of the problem. So in a general setting, you don't know how many clusters you're looking for. And also in that setting, actually, you have weighted correlation clustering. So also there are like weights, it's a real number on your edges for the weights. And actually in the setting here, we only consider the setting of unweighted correlation clustering. So we only have plus one or minus one for the weights. So there's no there's no weight in that sense. Only plus one, 0 or minus one if you consider a complete graph, and then to an arbitrary graph setting.
Jordi,
yeah.
I get a question from the chat if you can repeat questions that are asked in the room, because
oh, sure, yeah, that's
usually not so.
Yeah.
For next time.
Yeah. Okay. I'll do it for Koen's question.
Tested here.
Yeah.
I was wondering if you would just subtract the W plus and the W minus from each other.
Yeah.
Would you end up with similar results, or could this problem be really distinct from that case?
No. So Koen is asking if you subtract the W minus W plus from each other, if you get a different problem. No, you get the same problem. So then you get a single weight that actually indicates whether you want to be together or not be together. So it should be similar. Yeah.
Thanks. So you're optimizing over this C?
Yeah, exactly. Yeah.
And why is it integer in your problem?
Oh, because you basically, so if mapping is actually giving a number to a certain node that indicates the cluster. You give a number from 0 to n minus 1 for n nodes that indicates the cluster. And you can have as most n clusters. So then you basically integers that actually indicate the cluster that your node is in. Yeah.
The weights are fixed, right? This is not
yeah, the weights are the input of your problem. Yeah. Yeah. Oh, sorry, you won't ask if the weights are. Okay, next time I will. I will repeat it. Yeah.
But sorry, so but the number of clusters is not part of the problem.
No, so that's actually a variant to the problem. So you have different variants, and actually, in like the general setting, the amount of clusters to the problem, I won't forget it. it's so unnatural. So you've asked actually the amount of clusters that you want to put the nodes in is actually part of your problem. This can be, but it's in general not the case. So you don't know how many clusters you want to put them in. Only you know that there are at most n of them, and it's actually also part of your solution.
Joris asks if the weights are given by pre-processing.
Yeah, so in actually the practical example that I gave, the weights are actually given by pre-processing. But in this, yeah, those are part of the input to the problem.
Do you know if the problem is NP-hard?
I'll come back to the next slide, of next part. So usually in this kind of optimization problem, we have this notion of the approximation ratio, which I will also use throughout this presentation. This alpha basically means that if opt is like the optimal value of our function that we can have for this problem, then the solution we get is this x star, and then the function evaluation is x star divided by the optimal value in the maximization setting is then a value between 0 and 1, where 1 means we perfectly solve the problem, and 0 means we basically have like the worst solution you can ever think of. And this is actually a notion of how good you are in solving the problem's approximation setting. Now move on to the hardness. So this is indeed an NP hard problem to approximate on both the weighted and unweighted graphs. And in fact, it is known that so whenever you want to get an approximation ratio larger than 79/80, then it will become NP hard. So in effect, it's actually APX hard in that case. And it also differs for the min disagree and max agree version, but we will only be concerned by the max agree here for this remainder of the talk. In the best classical approximation algorithm with a guarantee on the approximation ratio it's able to achieve in the worst case is created by Swamy in 2004, and it gets an approximation ratio of 0.7666. And so there's still a large gap between what you've actually proven to be from when it's actually becoming NP hard to approximate further, and actually was achieved by the best approximation algorithm.
But this is a guaranteed lower bound.
Yeah.
So does it work pretty well in practice, or is it?
So it works pretty well in practice, but it's usually not used because it scales, I think, as n to the power n squared or n to the power 3, and a lot of heuristics they scale better, just with n, and they can go up to like hundreds, thousands of nodes. So those are usually used in practice. People are actually interested in very, very large problems. Actually, somehow then it makes less sense to compute this in this problem. People solve problems up to 100,000 of nodes, but anyway. Jordi?
Is there a natural link to maxcut?
Yeah.
Very similar. The approximation is different.
Yeah, good point. So if you actually consider the variant where you actually specify the amount of clusters you want to solve the problem with, if you consider 2 clusters, then of course you get the maxcut problem. It's equivalent.
But then as a follow-up question for that, it's I think known that the approximation rate you can achieve below 9/10. So
yeah, true.
How does that not apply to this setting then?
Because it's more general. Because if you for example consider for here you also don't consider the amount of clusters as an input that you want to solve for. And so only for the specific case where you have like 2 clusters you want to solve for, then you know you can actually use the result for maxcut. But for the more general case, it won't work.
Maxcut and upper bound on approximation is also.
But the problem is
because it's weighted.
But now the problem is different, right? For maxcut, you only consider you have a collection of nodes to create them in 2 different subsets. But here it can be any n subsets. So it doesn't directly translate to the general correlation cluster.
Yeah, but I mean, like for the specific case of 2 clusters,
yeah,
it's already known, but maybe that's because of the weighted thing in this data. It's already known that for maxcut, the most you can achieve is 9/10 as well. But here, so that would result in 1/10. Maybe that's.
Oh, you mean here for the 79/80? You mean that part? Yeah, that would actually make sense. Yeah.
But that's not empty.
Oh yeah, but yeah, it's only unique games conjecture.
Actually, I think with 9/10 it's also empty.
But is it under unique games conjecture or?
I think in the unique games conjecture it's tied to the best approach to the Turing units.
Yeah.
And without games, there is like a 0.02 difference or something.
So this result also doesn't assume the unique games conjecture, but if that one also doesn't, then
But maybe
that's a good
because
point.
Mexico has to be weighted for this to be FP hard, and this is the unweighted set.
Yeah, so for weight and unweighted here, the result is the same.
Okay.
So, but that's a good point. Yeah. Okay, interesting. Yeah, but it's from literature, so. So yeah, I already mentioned a lot of people in practice actually use heuristics to solve this this problem. So now we have our problem definition. Then move on to the quantum algorithm. So we chose to actually use the quantum approximate optimization algorithm to solve this problem. And what it actually does, you have an optimization problem over some domain f, some vector function value, vector function f, and then it maps. The QA is characterized by some depth p and some parameters gamma and beta, which are both also of length p, so contain p real numbers. And then what it does, it starts with some initial state, which is usually taken to be the uniform superposition. You have to define some cost operator, which is actually the time evolution of some cost Hamiltonian HC for some time gamma I. So every different layer, the time evolution is Hamiltonian is actually different. And this cost operator is just a diagonal Hamiltonian. So this eigenvalues actually represent the objective function value that you have. So every basis state that you have in your matrix, at the same place, it would actually, the number that's actually there in your matrix representation would just be the evaluation of the cost function for this this basis state. We also have a mixing operator, which is dependent on this beta, and that actually should depend on the structure of your domain that you're trying to optimize over. And again, we have some Hamiltonian actually defines the structure should be linked to it. And then again, we do some time evolution within now from time beta. And finally, with QA very simple. It's just a variational quantum algorithm with a specific ansatz. Start with initial state, you apply these cost and mixing operators back to back for time specified by these gammas and these betas. You end up with some kind of state that you should try to measure, and that's all the algorithm does in the non-variational setting. And the goal is to obtain states gamma beta to give actually bit strings that you measure with high probability of good bit strings, as in having a high with the function value with high probability. Usually this is actually adopted in a variational approach. So then what you actually try to do, you run the circuit for certain values of these betas and these gammas. You try to measure, you measure a lot of these states you get out from the distribution of your final state. And then you're gonna estimate the expectation value of your cost Hamiltonian, which is an expectation value of your superposition of states you actually created. And then you're gonna take that as like the cost function you want to maximize or minimize what you're trying to do. And then you tune these variational parameters just by using a classical optimizer that takes like the stochastic function value of this expectation value of the cost Hamiltonian as input. Then you hope to get better and better solutions if you increase p and also get better values for these parameters. That's a very simple algorithm. And so just defining fp as being like the expectation value of this cost Hamiltonian of the state that you've created with this algorithm. And the best possible expectation value is then defined as MP here. So the difference for different P. And then it's in the maximum over the gammas and betas that you can put in. And some properties for this MP. I mean, it's very easy to see it actually. If P becomes one larger, you should always be greater or equal to what you had before. Because you can simply pick the parameters to be 0, you just apply the identity, get the same results you had before. One can also show actually in the limit of P going to infinity, you can actually, in the perfect setting, approximate quantum annealing for an infinite time. In that sense, you should be able to perfectly solve the problem. But as P going to infinity, also your runtime goes to infinity, and therefore it's not really any use for it, except for just showing that actually in the limit of P going to infinity, you actually should be able to find parameters to actually perfectly solve the problem. So the runtime is linear in P, polynomial in problem size n, and as we shown last year, it's finding these parameters, gamma and betas, NP hard in the worst case. I would actually, in fact, argue that it's actually QSumme hard in the worst case, but that's a different story. But we do have some concentration of parameters across instances, which we also confirmed in our studies. This basically means that actually for very large graphs, if you're able to solve one graph really, really well and find some combination of parameters, you can just perturb the graph, make all kinds of different graphs and probably the same parameters. will actually give back approximation rates that are still pretty good. So that actually would mean that you can only solve the problem like once very, very well, and still get good approximation ratios using the same parameters. Yeah, Ronald, question?
What exactly does runtime mean? So the red and the blue boxes
Mhm.
have some e to the I, some
Yeah.
Hamiltonian. These
Yeah.
Hamiltonians could be kind of complicated.
Yeah, usually they're extremely simple because this cross Hamiltonian is completely diagonal. So you only have like products of Pauli-C operators.
But even then,
Yeah.
the number of entries there is
Yeah.
exponential. in the qubits.
No, true. That's
So in
true.
general, implement this as a unit.
Yeah.
Exponential gains in qubits.
Yeah, but you are usually also able to efficiently write down your function value, your function, sorry, your classical optimization function.
They're
So I-
they're too low.
Yeah. No, not always, right? So in our problem, they are always too local. But for example, for MaxQuit, they're also too local. But in general, it depends on your also on the locality of your objective function. If this is always too local, then also your implementation here is too local. But yeah, but I get if you're indeed your so it's the number of blocks. That's a better way to phrase it. That's also of course linear MP. And
The cost of HC would just be comparable to classical cost, right?
yeah,
Objective. Compute it and then you just add a phase depending on it.
Yeah, I mean, if you have a small circuit of the future.
But you need that class to be as well.
yeah. That's fine.
Adversarially defined problems that are sort of, I would say, exponentially large implementation of this
Yeah. Evaluation, you mean?
And the mixer you can also pick it up. So the synthesis for the mixture just in that notation.
Is the point of the algorithm to compare the ground state of this HC?
Yeah, that will be ideal. Yeah.
But I don't understand, like, why do you need this HC, this red boxes basically there? Because, like, aren't you just trying to parameterize all possible states and just compare the states?
Well, not all possible states. So we're basically it's basically just an ansatz for your VQE. And yeah, it's just people. The idea is actually you apply these phases just depending on your cost function.
Is it like related to the problem?
Yeah, exactly. So that's also what they use to actually show that the limit of p going to infinity. Then it actually, so it's more like say the better you always evolve from like one Hamiltonian to another one. You do like back-to-back applications of two different Hamiltonians. So usually also they take like the mixing Hamiltonian to be, for example, the starting Hamiltonian in adiabatic evolution, and the final Hamiltonian be like the cost Hamiltonian. And instead of just evolving like continuously from one to the other, here you do like back-to-back applications of both Hamiltonians. This is what you can do is actually to prove that actually p going to infinity. You can approximate the adiabatic algorithm, therefore use results from that to actually show that you can get back the optimal solution for some collection of parameters. Done. That's what we don't know. That's a question. Yeah. Oh, yes. So, I mean, the runtime is never about solving, right? So here, just approximating the problem. So I can just run it for p is 1, get like a probably pretty bad solution. But then the runtime is still on p, but it all depends on how good your approximation ratios you get out. Yeah. So we don't actually solve the problem. I mean, it's NP hard, so we cannot hope to do it. Yeah, some state. Maybe I'll just quickly skip over this for the time.
By the way, one more question.
Yeah.
So, are you sure that the number of optimization rounds you have to do is also following up?
You mean the optimization? Okay, Jon asked the number of optimization rounds. Yeah.
Yeah. Okay. Thank you. But here, how can you be sure that convergence will occur within the time order of p and n?
So we don't know. So the whole point is we don't know if we converge to the solution, right?
Right.
It's just that we have some ansatz and we hope to create good states with it.
Okay.
And we know that eventually it will converge for some parameters. We hope maybe we cannot even find those parameters because if the parameter finding itself is NP hard. So it's all yours in that sense.
You just run it and hope for this.
Yeah, exactly. Yeah. That's exactly the point.
Okay.
Yeah. But of course Yeah.
So I guess
But I will also later show there you can actually also analytically show some approximation ratio bounds, lower bounds, for example. So it's not all heuristic. But yeah, that's the I think with this variation of quantum algorithms in general, the
well, I mean, usually
yeah.
people they like impose conversion bound where if at some point your solution doesn't change enough, then you just stop. But it's not. This doesn't necessarily happen over a fixed amount of positions.
no. What I will later will show that already PS1 for some graphs you can actually already get for some parameters like an approximation ratio bound that holds for all graphs. I think this property. But in general, it's just you just run it and you hope that every time you increase your P with 1, you can hopefully get better solutions because you actually find better parameters which you don't know. All right, so
Speed.
maybe I don't know. So it also will become apparent later why we do this. So this problem naturally seems to lend itself for qudits because for every node, actually you want to assign a cluster which can be between 0 and n-1 if you just consider the labels being integers. So it makes a lot of sense actually to consider a qudit system where every node gets its own n levels actually, and every level will correspond to the cluster label you assign to the node. And it also become later clear why we actually chose to do this because of hardware constraints. So again, consider a graph with nodes at v, HSE. But then we have not just a bit string, just an integer string z, where every node gets its own z, which can be between 0 and n-1 integer values. And yeah, basically these qudit levels encode the different labels of these clusters for these nodes. And again, we've taken uniform superposition, now no longer for qubit states, but for qudit states. We define a cost Hamiltonian. It's also really simple. So for every term what we actually want is the following. If both qudits are in the same cluster, then it should just output a -1. And in the other case, so if there are different clusters, it should output a +1. So that's just a diagonal matrix that actually encodes the two-body interaction between nodes u and v. And if we then create the cost Hamiltonian summing of all different actions multiplying by the weights, then we actually this encodes to some extent the correlation clustering problem. Maybe to illustrate, so in the maximization setting, the weights from was +1, and no, sorry, we're in a minimization setting, so we want to minimize. It's a bit yeah, because in physics we actually do it, so we actually chose to use the minimization setting. So if QU and QV are in the same cluster, get back a -1. If the weight is +1, they want to be together, you get a -1 contribution to the total cost function. And if you then minimize, it's just good. So this is basically the intuitive way to view this.
Okay, so these weights are allowed to be negative.
Yeah, so these weights in this setting are always +1 or -1 in our setting. So we don't consider just arbitrary real weights anymore, but just only -1 and +1. Or basically 0 if there's no edge, but then it's not really.
Question about
Yeah.
The little HC, does it depend on a particular UV?
Yeah, it depends on U and V. Yeah. Sorry. So it's HC, it works on a subspace where these qudits U and V lives in, but it's the same for every U and V. But if you write out the whole, if all the tensor identities that you have there, then yeah.
Something very confusing about this quotation. So the little h sub c on the right hand side. Does this depend on a particular UV? Because otherwise you just minimize it to some.
I think if you just write down little hc and then just imagine some brackets,
Yeah.
A, v, then
So the point is actually this term operates on qudits U and V.
The HC, the definition here of Hamiltonian, it only depends on V, right?
Yeah.
So I'm clear from the notation now. Is the basis for this big matrix all H's?
No, it's on the qudit. So it's the nodes. The qudit code the nodes. It's on nodes. Well, actually, it's the cluster labels you assign to the nodes.
So So for every node you assign the
Yeah, so for every, oh, so sorry, no, the weights are actually on the edges. It's for every node we have like it's qubit level encodes which cluster it is in. But yeah, the weights are on the edges. The whole point here is actually since we have like a two-body term operates on the nodes, on different nodes, and actually the operation is the same. In this h of C, the small one, is actually the same for all nodes, but the weight is different for different nodes. So that's actually why for the total Hamiltonian it is different. But you can also incorporate, of course, this weight in this small h and sum over those. Maybe that would be a better notation in that sense. But hopefully it's a little bit clear. And this mixing Hamiltonian basically wants to allow transitions between different qudit levels, which is indicated here with the blue arrows there. So it's a convention in QAOA. After applying this Hamiltonian to allow transitions between different levels, and this R actually indicates to how many different neighboring levels you can actually transition. So if R is 1, you can only go to next nearest neighbors in like but also with periodic boundary conditions. So if you're in the 0 state, you can move to a 1 or to the d-1 state. And if it is larger, or from it's 2, you can go to 1 and 2, and d-1 and d-2.
There are no positive negative weights like you had before. It's just a single weight for the edge.
No, exactly. Yeah, it's a bit confusing. So in literature, they usually consider two different weights, but you can also consider just a single weight. It's just positive or negative. And from now on, we only consider weights being +1 or -1. So then on to compilation, so processor design and gate implementation. So for this, we consider a Rydberg platform. And Rydberg atoms, they are actually characterized by having a very high principal quantum number. And with this comes actually the large dipole moments. It also scales as n². This allows for very, very strong interactions. And this originates from Balmer trying to explain some spectra of the hydrogen atom. And then it's also there's actually further exploit of research by Rydberg in 1888. Actually, they wrote on this formula with this 1 over this lambda is actually the lambda is the wavelength, R of H is some Rydberg constant, and those n and m are two quantum numbers, or this n is the principal quantum number. And you can basically view a Rydberg system or Rydberg atom as being like very much hydrogen-like. So you have an atom core and some electron which is very, very, very far away from this atom core. So this, if you consider this one total to be the Rydberg atom, it's very, very big. So this can be large than several hundred of nanometers. And from this you can also create systems that can be used for quantum information processing. And usually what they do, they create an array of these Rydberg atoms. And you have then lasers actually that hold these atoms into place, which are then called tweezers. You also have single-side traceability, also with some other lasers. And these tweezer lasers are very much detuned, so they don't actually interact or allow for create transitions or like excitations of these Rydberg atoms. And the governing Hamiltonian for describing the ground states interaction or the coupling with those Rydberg states, the states actually are very far away from the atom core, is governed by this Hamiltonian. And the first term here actually describes the interaction between the ground state manifold and the Rydberg states. You have a potential and here long-range interaction. And you can see that the first and the second terms, they only work on like single sides. So they only sum over for this particular ice. And the last one is actually this Rydberg term, which actually is a multi-body term, so two-body term. And this allows for long-range interactions. And this V is also one of over the R to the R6. And actually, this one can be used to create two qubit gates, as I will explain briefly now. So for creating two qubit gates, use something which is called the Rydberg blockade, which is written there, but you cannot see because of the zoom over that. So assume now, or consider two. So these are two different Rydberg atoms, and we have like this ground states being 1 and 0, and another state which is very, very, very far away spatially, which is this Rydberg state. And then if the control atom is in the 0 and the target atom is in the 1 state, we always apply the same sequence to do these 2 qubit gates. I won't explain what these pulses are, but these are just laser pulses. You just have to, from now just assume that they do something which is actually useful for us. So we have this pi pulse we always apply, do a 2 pi pulse on the target atom, and then another pi pulse on the control atom. And the whole point is here, so if this pi pulse, it cannot reach the Rydberg level, it won't go there. And if you then apply this 2 pi pulse on the target atom, for some reason actually it picks up a phase shift of pi. Which is then basically the thing that we did. And now we assume, or we consider the target atom to be in the 1 state, and the control atom in the 1 state, and the target atom as well in the 1 state. And if we now apply this pi pulse, it will be excited to this Rydberg state. And this Rydberg state actually creates some Rydberg potential, so this V on the target atom, which raises this energy level of this Rydberg state for the target atom. Now it can no longer actually reach this Rydberg state. If we apply this 2 pi pulse, then again this pi pulse on the control atom, and then it picks up no phase shift. So depending if the control atom is in the 0 or in the 1 state, it either picks up or doesn't pick up a phase shift. And this allows us to actually create some kind of CZ-like gate, which can then be used to create 2 qubit gates.
It's an inverted CZ gate.
Yeah, exactly. It's not exactly a CZ gate, but we can just do a single qubit gate, like the single qubit interaction that I showed before in the Rydberg Hamiltonian. Then you can actually convert it to CZ gate or V0 gate or anything that you would like for your quantum computer. So we consider fermionic strontium as being the actual system, physical system we're going to use. And so, advantage of fermionic strontium is that actually it has 10 hyperfine states in its ground state manifold, which can then be used all as different qudit levels. So in total, we have then 10 qudit levels we can actually use in our problem. We also don't have to use all of them, so we can also tune between different amount of levels that we use in the system. All the advantage is actually that we have very large coherence times for these systems. And a lot of technology is also being already developed for fermionic strontium. They are, as I've been told yesterday, the best atomic clocks in the world that we currently have. And this picture basically then shows, so on the left side on the A part, it shows all these different state manifolds we're going to use to actually create the whole recipe of building this quantum system. Actually, it's going to execute the algorithm. So here you have this ground state manifold, this 10 different hyperfine states we can use actually encode our qudits in. There's the manifold here, this 3p1 actually is used to actually measure the system. So we first have to excite that system before we can actually do the manifold before we can actually do the measurement. And those manifolds all the way up, so there's 1p1, 3s1, those are our Rydberg manifolds. And those are actually used to excite those Rydberg states to create, for example, these 2 qubit gates we just talked about. And there's actually 2 ways to go there. So one is by this purple arrow, it's a single photon excitation, which needs, I think, very large, it has very high demand, which you should be able to do. So usually we allow for transitions between a different manifold. So there's 3p2 manifold. So you first excite to that one, then excite to this Rydberg manifold, actually go to the Rydberg state that we need in order to create these gates. And in B are all the specifications that you would need if you would actually work with the system, which I think for most people here is not that relevant. And in C actually we see here, so this actually, so this cat S denotes the manifold here, the cat P denotes the manifold where the not dark but lighter red arrow goes to. This manifold can also be used directly to create 1 qudit gates, which we also use to actually create 1 qudit gate. So then we excite the manifold, use some laser pulses and go back. From this we can actually create the mixing operation that we need in our algorithm.
So what can I ask? What's the difference between the R is 1 and R equals 2? What is R?
Sorry, what do you mean?
In picture C.
Yeah.
There's 2. It looks like there are 2 separate cases.
Oh yeah, good point. So I skipped on this. So I actually did explain in this mixing Hamiltonian, there was like this sum over phi going to R, right? And it does indicate, this indicated for your mixing, if it only considers nearest neighbors or also second next nearest neighbors. So basically, if you have mixing from the 0, for example, you're in the 0 state, qudit state. If the mixing can go from 0 to 1, or 0 to 1 and 0 to 2, or 1 to 3. So this is basically what this R indicates, like how much mixing you have in this. How much it mixes to nearest neighbors or further than that. And on the hardware, we only worked out RS1 and RS2. So only mixing between nearest qubit levels, next nearest qubit levels, and those are like the recipes, like these indicate like pulses that you have to do operations, actually implement these different mixing operations.
Okay, you do that with sort of combining two of resonant pulses, it seems.
Yeah.
Is this picture A? Where are the 10 levels that you mentioned?
The 10 levels are here. So yeah.
Are they the red one? I mean, there's more than 10 stripes there.
Yeah, so I think like so it is 9 over 2, and actually the number of levels is just 2 times 9 over 2 plus 1, which is then 10. But
maybe I can ask you.
yeah. So there are like hyperfine levels in there. So that's
We have a student who's doing a project on this, so we'll
Yeah.
have to ask you some questions.
yeah. So if you go do that, I'm probably gonna forward you to GC, which is sitting here.
The left drawing, so each of these black lines contains, like as Jordi said, 2 times the number which is written plus 1 sublevel, which is not shown. So like the middle picture is kind of the zoom on the red highlighted black lines. So you have like many levels.
So essentially there's a tensor product between the 10 levels of the hyperfine states and the levels in A picture, is that right?
Yeah, well, I'm not sure if I would call it tensor product, but like it's just a drawing. Yeah, so the black lines on the left drawing, if you zoom into each of the black line, you have all these sublevels, and the number of these sublevels is indicated by this like number whatever of the
Times 2 plus 1.
so you have always like 2 times the number which is written plus 1 sublevels.
Yeah, and changing between states in the A picture doesn't change the number 0 to 9 on the right hand picture.
Yes. So the 0 to 9, those are actually in here, right? So that the cat S indicates a manifold here. That's those 10 levels, and the cat P are actually levels in there. So 3v2.
Oh yeah. Okay, so if you want to go to A, so you have to do something clever. If you use sort of option R equals 1, if you want to go up to the Rydberg state, you might mess up the hyperfine state, unless you do something smart.
Well, this is why we use all this thing, because you can do this state selective. Because you will be able to tell to now I don't know if you have qubit level of 0, 1, 2, 3. And this is precisely the system which allows you to do it using selection. So you have this, system.
Yeah, good.
Yeah, thanks.
Yeah, so I won't go into detail of this, but from this you can construct just building blocks, which are basically this sequence of laser pulses, and you can create all kinds of gates with this. And also have like these recipes actually to create these different gates. And from this you can go back to your algorithm, consider all different aspects of it, so the initial state creation, those time evolutions, these costs, and these mixing Hamiltonians, the measurements, and then you can get like a full recipe that you actually need to have in order to implement this on the actual quantum computer. So all the way from initialization, so creating this supervision of these qudit states, cost gate, mixing gates, but also stop operations. Measurement, it's all basically in there. So basically we've done everything you need to know in order to run the experiment. So then performance analysis. So the first part actually we will consider just small instances and larger P. So this will be guided by numerics. And basically we create all kind of math optimization strategies to actually make the numerics give out better results. So these are like very common things in optimization. We use restart, so restarting the algorithm at different initial points, but also actually I already told you about this concentration of different initial points. So once you found a very good initial points, probably it will also work well for other graphs. So we also optimized, like for one single graph instance, we really optimized like a lot of the initial points. We could actually get a very good solution back and use the same optimal valuation initial points for other kinds of graphs, which is also very common in QA literature. but not so much when I started. One of the most important ones actually is loop over cluster numbers. Also in its hardware, you can actually change how many of these qudit hyperfine states we use. Actually, you can actually imagine, for example, if the optimal solution, this correlation clustering problem, only needs 2 clusters, it's kind of useless to actually search over a Hilbert space, actually uses 10 qudit levels. So why not run the algorithm for just using 1 cluster, 2 clusters, all the way up to n normally, but we can do this, we could have done earlier. And then you see what you get back as a solution, then just keep the best one of this. I mean, this does increase your runtime as another factor of n, but for small numerics, we don't really care. And the choice to classical optimize, we did a study just comparing all kinds of classical optimization techniques to actually improve it. And this graph just shows what we of course would hope that actually it would go up a better approximation ratios if that added improvements. But let's not go too deep in this. All the results and confirmation of things already known in literature, classical optimizer study. And what we actually found, we can only go to problem size of containing 7 nodes, so really, really small, because your Hilbert space is actually really, really big, because you have 7 to the power 7 amount of possible classical states that you have to actually encode your problem. But we actually do see, so the Swamy bound is actually the worst case approximation guarantee that you have for the best classical algorithm. It has such a guarantee, and at least we didn't go below it. I mean, if we went below it, then it would be pretty bad. And for PS2, we could see actually that we actually are slightly above it, but it's only to some extent an unfair comparison because we can compare like a worst case bound for in the classical setting to these numerics that we did. But also the worst instance in our data set is still slightly above it. So maybe there's some hope, but at least it's not doing extremely bad on these kinds of instances. Yeah.
So when it says when you optimize over the initial points with p equals 5.
Yeah, it goes down.
It goes down.
Yeah.
So is that a general pattern, or is that for high p the initial points don't matter much, or is this?
I think the problem here is actually, so if you increase p, you get more of these variational parameters, right? And so also your search space actually increases in that sense, the dimension of your search space. So if you then use this, you can also imagine actually then this concentration of parameters, actually the distance to these points actually increases because this dimension increases your search space. So
I mean, you maybe need to do more iterations on this.
yeah, so if you just have like if p is only 1, you just have like you can just draw like a 2D grid where you then search over your parameters. If you have like 1 single point, actually very good. Maybe you can imagine actually then that the optimal points for other graphs are like in the neighborhood. So then your points will work really well. But if you increase the dimension, maybe this is actually increased. So this concentration of parameters becomes less and less important, increasing p.
And did you try to compare with like not just this Swamy bound, but like with the best classical algorithm, like the rest of it?
Yeah, we didn't do that, but I feel like that it should have been. I mean, that's a very natural step to do, but you can only go to like NS7, which is actually really, really small. But for us, you don't really, like in the worst and average case, it doesn't show that much like an extreme dependence on like small instances. So I would expect that these heuristics would always solve the problem perfectly well for these really small instances, because they're just that easy. For the QA, it seems to be that it's actually not, already for very small problems, you already see that actually it can already like struggle to solve it well, but if you increase the problem size, it won't like suddenly transition to being extremely a lot harder or not. So at least that's for future work, actually in comparison with actual experiments, where you could actually consider, for example, 50 nodes. Then it would make more sense, I feel, to also consider heuristic comparison. Rules.
So the third comparison, you sort of want to compare a quantum run with a classical run with a certain classical time run. So these two are comparable. Because probably for the classical heuristics, if you just give them more time.
Yeah, true.
So how much budget in terms of runtime do you give the classical?
Well, we don't even consider classical algorithms runtime here, because we only consider like a worst case bound that we have here.
I could imagine that the Swamy one works better if you give
So the Swamy algorithm actually what it does works the same way like on an intuitive level, or like use the same process as Kuhlmann-Williamson. So you have like this interlinear program that you convert to a linear program, and you're going to solve it, and then you're going to do some randomized rounding procedure to actually get a solution. And with the randomized routing, of course, you can always increase the time. So you do take more of these samples and probably get a better approximation ratio. So this one is just an expectation value. So it's just, if you take a single sample, a single randomized routing procedure, what an expectation does it give back? So yeah, then if you do it longer, then of course it will go up. No.
If you talk about worst case performance, do you know what instances are really hard?
Yeah, we actually do know that. I don't show it here, but the instance that actually finds really hard are those actually that need a very low amount of cluster numbers. So only uses two clusters. Those seem to be the most difficult for us.
And have you, wait, are they in general really hard for heuristics, or are they hard for your algorithm?
I don't know. I think I don't really know for sure that it's for our, and it's actually hard.
Sorry, just you might have said this, but just for reference, how many runs do you do when you take an average and take the works?
So those are over graph instances. So we consider, so those are for Erdős-Rényi graphs and for complete graphs. For some reason the legend is gone here. And we consider 50 of those instances. We actually, we give them, so we create those instances from complete graphs, so it's complete, very easy. And then we give them edge weights being +1 or -1 according to some probability. And probability is actually not chosen with a fixed probability, but we change the probability of having an edge weight +1 from 0 to 1, actually we sweep over it. Because you can imagine that if you only sample with a fixed probability, then always you will roughly have the same amount of plus and minus edges. So so you always consider like a similar type of graphs, but you also want to consider graphs that, for example, have almost all edges +1 or all -1, because those are like very different correlation clustering instances. So we actually try to, with the sweep, actually consider the whole spectrum of possible correlation clustering instances.
So you do not when you simulate them, you do not first generate clusters and then generate a graph from that. You randomly sample with different probabilities.
That would actually make more sense if you consider like very large graph instances.
But for here,
we go to NS7, so that's
So if I may ask an annoying question.
what if I say no?
I was just wondering how representative and what's the other one?
Complete graphs?
Yeah. How representative they are for the parts description problem.
Not at all. I mean, for this practical problem, I mean, in the practical setting, people consider these heuristics on like graphs that have like 100,000 of nodes, if not more. And also like this neural network. I think we had talked with Bosch and think the smallest instance they could actually create that somewhat resembled the realistic problem, at like 30 nodes or so, but it's still extremely far away from what we did.
Right.
On actual hardware, I think they have like 50 qudits. We could actually try to do an experiment actually in realistic instances. But what we can simulate is like this qudit and surf, it's just way too small.
Okay.
No.
The Erdős-Rényi graphs, they exhibit these phase transitions, right?
Mm-hmm.
So if you assign +1, -1 equal probability, I guess you just get tons of clusters, tiny little clusters.
Yeah.
But if you transition towards like more and more biased distribution, I think what happens is that at some point, if your graph is really, really large, you'll all of a sudden see like a few pretty big clusters.
Yeah.
And at another point, with very high probability, you just see one big cluster, right?
Yeah, of course. If you're almost always assign an edge +1 weight, then it will probably want to be the same cluster.
For these Erdős-Rényi graphs, you really only need to consider maybe two interesting distributions. Where you find like either one big cluster or a few bigger ones.
Yeah.
But if you're far away from those, then either there's really nothing to find, there's no science whatsoever, or it's trivial in the sense that basically it's one big block.
Yeah.
But I guess maybe you didn't observe that because you're working with very small.
Yeah, I think that's the thing. So if we were to go to bigger graphs, I would also not use this method. I would just like what he also did for another project is try to on beforehand like create clusters, and then create like edge between those clusters, and then basically this would be the problem actually to solve. But then you actually artificially can generate a cluster setting actually based on what you think should be the cluster. Even though it's not optimal cluster, it would still be like will be more interesting because then you can actually really put like clusters in there. Whilst here, which you already mentioned, it's very often just or it's a single cluster or like all not in the same cluster. So it'll be more interesting. But I think for 7 nodes, it's not really that important. Yeah. Yeah. No, true. So I also have to watch the time. So maybe just quickly go over. So now we're going to the more results. So actually, we also have a proof that actually shows approximation ratio bound for QAOA. Before was only known for max cut. So I think we were the first one. Also another problem. We're the first one to show like an approximation ratio bound. And so we conjecture it's still very much below the 0.7666. And it also holds for 3 regular graphs. So it's only very, very specific. And I will not go into details on how we showed this. But basically the key idea is actually that so this QAOA energies expectation values as cross Hamiltonian can be decomposed to sum of individual edge contributions. And each individual expectation values energies are determined by the subgraph with most pH away from this edge. So for PS1, you only have to consider 3 different subgraphs because our weights can only be +1 or -1. The total amount of subgraph configuration is actually relatively small. It can then be evaluated. Well, through a minimax linear fractional program, try to solve it. You have to relax it because we cannot solve it, and then we get some conjectures and lower and upper bounds. And actually, our upper bounds actually matched by some numerical simulations that actually don't use this relaxation. So we're pretty confident actually the actual bound is 0.667. And something else, more on the hardware level, you can imagine that. So what I mentioned already for this qudits, it's very natural because if you have a two-body interaction, you have that two qudits have to interact with each other. But for qubits, if you want to encode these qudits, which you can of course always do, you might have to have some kind of blocks that actually encode these qudit states. So if you consider a processor geometry of just being triangular, hexagonal, then so every intersection here or crossing you can put a qubit on there. If you want to use a qubit system, then you have to create these kinds of structures where you, for example, you use the log 2 of d. If you have a 4-level system, you have to use 2 qubits actually encode this qubit system. And the interactions, also some operations, can get a little bit weird if you have, for example, a two-body interaction. And from this, you see that a lot of work actually show that in the setting, considering the best of current qubit encoding for this problem, that if you look at the leading contribution in terms of the amount of edges in the complete graph setting, actually we get like a very small, really small constant factor improvement over the amount of 2 qubit or qubit gates you have to use. Then again, this is really a fair comparison because it might be that to perform these gates, also the times are different or the complexity is different, but still, it's still I think a funny result that actually this qudit formulation in the setting helps slightly, and in this setting that's might be useful at some point.
So this is basically considering that you swap the entire thing.
Yeah, so this considers complete graphs, and you have to, so this complete graph cannot be simulated on like these hexagonal geometries. So then you have to do swaps. You have to swap this whole block around, or like you have to come up with some kind of swapping procedure if you want to do a 2 qubit interaction. Because if you want to have interaction between like the upper one, you can have this 1-1 interacting 1-2, but not the one with the 2 in the red, for example. So you have to do an additional swap. And
You always wonders why you're using triangular processor geometry.
Because it has the densest backing factor in 2D. Just to hurry up a little bit because I have to catch the last train before the storm. Because I'm missing my winter sport. And yeah, so finally some other results. So we had some generalized Pauli error model. We used that also again on complete graphs, and then so the identity then happens after every gate with probability 1 minus p2, and else we pick one over the d squared possible generalized Pauli unitaries that actually implemented an error on our system. We again then run our algorithm, then we already use the parameters that we found before. So we don't do any optimization here, we just assume that we've already done that to see how much the approximation ratio deteriorates as function of this error. And then we of course expect that the error goes down the performance goes down very quickly. And here we actually show what's kind of funny here, basically what Ronald mentioned in the beginning. So in the plot D, we actually show that, so on the x-axis we have the 1 over the p2, so 1 over the error, and on the y-axis we have the amount of gates we can do before we have lost half of the approximation ratio. There's performance. I mean, this is more like physics style. You try to make some plot and it fits pretty well. And it seems to be, but it does confirm the intuition that actually we had before and has been shown in a more rigorous manner in some other works where actually, so inverse proportional to the error, the amount of gates you can do scales with that. So if your error, so the error should actually become really, really small in order to not lose half your performance already with the algorithm. Just a quick back of the envelope calculations, and you can already see that so the species X like this fundamental 2 qubit gate we can do, and if you have then an error probability of 10 to the minus 3 for this 2 qubit gate, then we can only go in the lab to a problem size containing 30 nodes for complete graphs, and one order of magnitude smaller, 41 nodes, 10 to the minus 5, only 130 nodes, which are still really, really, really small. So this again confirms that errors are very problematic. But we have to make a side note here. This is some complete graphs. So if you consider like graphs very much native to actually your processor geometry, the result might be much more much better in that sense. So question?
So I think you just mentioned that you take the parameters that you got from sort of a perfect optimization.
Yeah. Yeah.
Do you know whether you looked at it or some other people, whether it's useful to actually consider the errors in optimization? Because you could imagine that certain results are more, some of the parameters have been some more error resilient.
Yeah. So the thing is, what is known from literature that actually, if you look at the optimization landscape over these gammas and these betas, so this errors only flattens optimization landscape. So parameters that are good without any noise are still good in the noise setting. But if it flattens, it might very much at some point get stuck. Like the gradient might very quickly vanish. You might not be able to actually find these parameters. But you were mostly interested in, even if you have like the perfect parameters, so you can just run the algorithm with I mean, not perfect, but good parameters, might you actually still be able to see like a good, might you be able to measure like good bit strings with good probability? And then the answer turns out for these complete graphs, that is still probably no. No. Sorry, I'm going over it really quickly for the results, but so for the conclusion, so we encoded the correlation clustering problem into this QAOA paradigm, specifically tailored for qudit systems, and we gave several improvements to the vanilla QAOA, and this is mostly guided by numerics, using meta optimization strategies. We also gave a proof and conjecture that actually, so our slightly modified QA version. So very important to note here, approximation rate only holds when you loop over cluster numbers. So you run your algorithm by using only one qudit level, 2 qudit levels, 3 qudit levels. Then actually you're able to retrieve the approximation ratio conjectured at 0.6699. And we then derived operation schemes for the Rydberg quantum computer, specifically from Ionic strontium. And we showed actually this qubit formulation is superior compared to like the best known qubit formulation in terms of the gate, 2 qudit or qubit gate count on complete graphs. Finally, analyzed algorithm performance in presence of noise corresponding to a generalized random Pauli method, and so the performance actually quickly deteriorates with increasing noise on these complete graphs. I'm looking for future work, so there have been development on like more novel QA simulation methods of actually be able to simulate extremely large the performance on extremely large graphs. Those only work for qubit systems. Maybe this can be extended to qudit systems, specifically our problem. New techniques are maybe needed to actually find approximation ratio guarantees for larger values of p. Because if you want to use our method for PS2, I think there's some back of the envelope estimation. We already need 10 to the power 7 hours of computing time, so that will not be possible. Yeah, maybe you can further exploit some hardware, the hardware constraints. So if there's long range interactions on these systems, you can use to implement non-planar graphs. Also, the unit disk graphs are very native to these systems, and maybe those unit disk graphs correlation problem is still NP hard, which is actually not known in literature. It's known for max cut, but not for correlation clustering. And maybe multi-qubit gates, something we can actually also use. Maybe just some other new software, hardware collaborations from which we can learn stuff from both ends of the spectrum. So now actually we showed actually numerical simulation for very small n, larger p what happens we have bounds for low degree. We probably now need an experiment in the near future to actually see if there's anything useful to be gained. Thank you.